Okay, good morning, everybody. It's my pleasure to introduce Ronaldo Laishram. I hope I'm pronouncing
Yes,
that right.
it is
Okay,
right.
okay,
Yeah.
okay.
Yes.
Ronaldo and I met in a protoclusters and clusters conference in Tuscany about a month and a half ago now.
Yes.
And it so happened that Ronaldo and I were also supposed to share a night on the Subaru telescope back about a week ago, and I think something happened with Subaru that might be familiar to us Geminites that prevented us from doing that. But Ronaldo also has a lot of collaborators here. Ronaldo is an expert in narrowband imaging. He's a PhD student with Tadi Kodama, who for many decades now has been one of the leaders in mapping out protoclusters and clusters with narrowband imaging, dual band or triple band narrowband imaging. And Ronaldo is working on density mapping, looking at intermediate to high redshift clusters and protoclusters and the chemical evolution of those galaxies. And he's going to talk to us about all of that work today. So please.
Should I start? Sorry. Thank you so much, Ryan, and Jamina for giving these opportunities. And yeah, so I will just go ahead. So yeah, before my topic is mapping the large scale structure and the environmental dependence of star forming galaxies. Before going that, I will just I'm from India and from Manipur, so one very beautiful place in like very eastern side of India. And I'm in Japan for last 4 years. Like I'm doing my PhD in Tohoku University. And yeah, this is our campus. Yeah, beautiful campus. And so we have lots of nice places in Japan. Yeah. So anyway, let's go to science. Yeah, and as Ren said, I'm working with Tadaki Kodama, and I'm also here. I'm visiting Yusei Koyama from Subaru, and yeah. So let's start. One of the my interests is I would like to understand how where the galaxies live, environment, and how they matters to the galaxy they start forming, and they are quenching. And so for that, okay, yeah, sorry. Before that, I will just give a bit introduction. So we know that galaxies are inhomogeneous in small scale. So they form a very large scale structure where we have a dense regions known as cluster, and we have filamentary structure, and we have the field or void region. So it's very important to understand how the galaxy's properties are changing along this structure, and lots of work has been done to in order to try to understand these properties. And so yeah, this environment is very important for their star forming and how they died quenching. So for that, lots of work has been done, and the environmental dependence at redshift 0 at the local universe is well-known study where it's well known that galaxies properties are strongly dependent on the environment. And so at the high density environment, we have mostly elliptical and not or Lichtenberg star forming all galaxies. But in the case of low dense environment, we have higher star forming, and most of them are spiral galaxy. So there is a proper dependence on the environment. And so it's well-known study that at the local universe, its various properties are strongly dependent on environment like morphology and SFR. But what happens at the redshift higher than 1? So now the redshift high redshift is changing with the ZWST, but I will now focus to above 1 for my talk. And so, and it's lots of work also been done. So in some case, like we have at the redshift 1, there is an increasing trend of SFR, which is the reverse to what we observe at the local universe. It's from Cooper at the 1, and this from Brian. So the group, so we found that there is a reversion of SFR and at higher redshift, which is reverse to the local universe. But in some case, there is also found out like in startup or Patel, they found that there is a decreasing trend of SFR with the environment where they found less star forming in the dense environment, which is contrary to the what observed in some of the study, so there is not a very clear picture of environmental impacts of galaxy evolution at a high redshift. And this may be because of the how we choose the environment, like projection effect and the selections and the different tracers. So yes, so this is very important. And now lots of work has been doing from many sources, but in order to understand when the epochs of this emergence of environmental effects, when did it started, it's well known that at the redshift 0 is well known, but at what redshift it started this kind of environmental effects, and what makes this environmental dependence is, and how they correlate with other, like how the morphology are changing and how the quench, chemical abundance, these are now a hot topic, and it's still an answer. Like this is kind of primary questions where we need to work. And one of the big challenges, if you want to study the environmental dependence, and one of the big challenges is we need to find a distance cluster so that we can study clusters, field, and yeah. And the distance cluster was very rare, but now non-proto cluster are increasing with lots of data. And we also need a large uniform sample of star-forming galaxies. So what is the ideal solution? So for that, as I mentioned, if you want to study the environment, we need a like precise environment, how the galaxy's properties are dependent. And the difficulty is the accurate determination of the redshift. And we have spectroscopic redshift, which is very ideal, but it's expensive. And if you want to observe the sample, will be too numerous to be observed. And it also requires pre-selection of target before observing, and we can introduce the sampling bias. And one of the most like efficient or easy way is like photometric redshift, which is very easy to get, but at the higher redshift, the uncertainty becoming larger. So then, what is the next solution for that? Narrowband imaging. So narrowband imaging is a very powerful approach to identify star-forming galaxies along the cosmic web because of their strong emission lines. So this narrowband filter will target the nebular emission from ice regions of the star-forming galaxies. So yeah, I will introduce a bit about the narrowband. So what narrowband did is that, so when the stars form, we have this from the young star, we have UV emission, and so it may trigger the nearest gas, and we have this ice alpha, and like this is one of the typical spectrum of the star-forming galaxies. We have lots of line like O2, O3, S beta. So what narrowband did is that we are trying to capture one of these emission lines with the photometry. So suppose we have broadband. So we have one big broadband, and then this will cover all the region. But when we do the narrowband, very small window, then what we will do is that, suppose here is one example, like this vision representation. We have the broadband, and we have the narrowband, and if there is a start forming like maybe ice alpha or O2 or O3, if there is upset, we will see if there is that kind of line, then we will see this emission line. So this is the one broadband images. This is the narrowband. As you can see, it was brighter in the narrowband, and when we use this broadband and the narrowband, we can get the emission lines. So this is how we capture the like start forming galaxies based on this strong line, maybe ice alpha or O2. And yes, narrowband is lots of work has been doing with narrowband, and the accuracy level is very high, like thanks to this very narrow slit, a narrow window, and it gives us an accuracy of delta Z of 0.03. But, and it also gives us the large sample size. So if we have the large, we can get the sample size and with the up to the limiting flux. So this is one of the very ideal solutions. Yes.
How you distinguish between a faint H alpha and a H beta? If you show the,
You mean?
yeah, you have you
Yes.
can have different lines.
Yes.
If it's start forming galaxy, you can have different lines.
Yes.
So you have another filter that you can use to map the acidity of the galaxy.
No, actually, yeah. Suppose like based on the narrow band, which I will also introduce later. So based on that, based on the like, because we already know the where ice alpha O2 are located based on the redshift, and we have this all the narrow band filter. So I will come to that part, and yeah. So I will come to that, yeah. And so before that, yeah. So this is this narrow band will give us accuracy of 0.03, which is good. But the thing is that the accuracy level of 0.03 this corresponds to the co-moving depth of 56 megaparsec at the redshift 1.5, which is very uncertain for measuring the precise environment, because the size of a cluster is like 1, 2, or so. This is not a very, and like if you want to do the precise environment, then this is not a we give uncertain environment. So what should we do? Then here comes we, instead of just one narrowband, we introduce, like we use a 2 narrowband. I'll discuss the methods and what later, but yeah. So instead of just one narrowband, we use the 2 narrowband filters, and yeah. So this is how we try to solve the, like, try to get the accurate redshift and also flux. So this is this method was introduced by our group, Hayashi-san, at 2014 paper. Then I used these methods in the one of the first time in the ICSC deep field. Yes, so I will come to the methods. Before that, but the Malvern looks like how we will capture the line. So the thing is that we have the narrow bands, this one. So based on the yeah, or maybe okay, I will come to that. Yeah. So before I will introduce the method first. So we have the 2 narrowband NB921 and NB920-6. So this is a 2 overlapping double narrowband filters, and there is a bit overlap with the slight difference in the response curve, which you can see here. So what we did is that based on the locations of the galaxy, like emission lines, it may be brighter in one narrowband and it may be dimmer in another narrowband. So suppose this is one galaxy, for example. So in this case, this is brighter in more bluer side, NB921, and it is dimmer in the NB920-6. So what is that? These 2 narrowband will capture the different flux. So based on this line ratio, and we from this filter response, we have this line ratio. It will give us the locations of the where the galaxy is located. So in this case, we have this flux, so it corresponds to the around based on the redshift, we will get it. So what from these methods, what we did is that we get the redshift, and we have some spectroscopic redshift at 0.4, and so here is the comparison between the our narrowband and the spectroscopic redshift. As we can see here, there is a quite a correlation between the narrowband redshift methods and the spectroscopic redshift method. So this is better than the photometry. Like if we compare with the photometry redshift, this is more better. And once we know the redshift, when we can separate the projections and the study the environment independence. So yeah, this is the methods which we will use for our work for the first case. And so for that, we have for our work, my first project was focused on the deep 2-3 field in the Subaru. Thanks, because Subaru is very wide. It provides us one of the widest in the deepest imaging data. So thanks to its filter, it can capture the clusters and even filament, and thanks to its wide field of view. And we used different catalog, like the photometric data from U-band to K-band to measure the stellar mass, and like this UCURT. Then yeah, so to measure the physical properties other. And yes, so I'll come to the questions very much. So you're asking about how we will know whether this is ice alpha or O2 or like those, right? So yes, what we did is that suppose in my case, we have narrowband NB921. So it is corresponds to the around 9,000 Armstrong wavelength. So it may at the redshift point 4 it may obtain the ice alpha line, and at redshift point 8 it may obtain this filter may capture O3, and at redshift 1.5 it will capture O2. So this is the with just this narrow band it will capture this 3 line at this 3 redshift. So what we did is that based on the available spectroscopic and color selection, we separate this 3 line, 3 of like ice alpha at redshift 0.4 and the O3 at redshift 0.8 and the O2 at 1.5. This is how with the color which is derived based on the available spectroscopic. So that's how we select this different line at different redshift. Does it answer your question? Or okay. Thank you. So this is from Koyama et al. And so using the same like NB921, as we can see here, this is the ice alpha line at 0.4, and this is O2 line at 1.5. So I will focus on the 1.5 for my first project. Yes, so as I described, we using our double narrowband technique, we can get the redshift, and so this is the redshift what we obtain. So based on that methods, at redshift 0.4 and the 1.5, as you can see here. And so once we know now we know the redshift, then we can try to get the kind of CDO 3D structure, because we know that redshift when we have the strength distribution. So here is the one of the 3D structure which is met with our redshift derivation, and this is one of the camera cluster, which is a red sequence cluster from by Ogri et al., known as camera cluster. So as we can see here, there is the overdance, and we have this kind of filamentary kind of lattice structure around here. And so this is one of the advantage of our method, that we can make this kind of 3D structure. Then other than is that we can also separate the structure. So this is at redshift 1.5. And you can see there is 2 kind of peak. So we try to understand, see whether they we can separate the structure. So this redshift slice 1, this is the structure, and for the slice 2, this is structure. So there is we can separate the structure. So if we want to study the environment, then we can reduce. We cannot completely rule out the projection effect, but we can somehow reduce the projection effect. So as we can see here, if we use just one narrow band, we will see this 2 of the kind of we cannot separate it. So this is one of the advantages, that we can separate it and we can study the environment with more less projection effect. So up to now, we using our novel methods, we find the accurate redshift, and we can make the 3D structure and separate the structures. Then let's go to the investigation of galaxies properties. So yeah, this is a redshift 1.5. Here I put the SFR and the O2. SFR derived from the O2 and local density. So for this density, what I did was we use the nearest 5 neighbor. So based on the location of the nearest neighbor, we like calculate the density. And we also apply the projection effect because of the based on the redshift, or by cutting 1,000 kilometer per sec. And so this is kind of reduced projection effect environment. And we see there is a not a strong but weak increasing trend of SFR density because of the less sample in the high density. But still, when I do the case test, we found it's not that significant, like at the borderline 105. No, yeah, from the case test we found the case this one. So even though the increasing trend is very weak, we check the SSFR, and we see no correlations between the density and the environment, density and the SSFR. So what we check the, because we found this increase SFR higher, a bit weaker, higher in dense environment. But so it may be because of we check the mass, like mass of how is the mass are distributed along this 3 density regions, and we found higher massive galaxies are more higher in the high density environment. So the every increasing trend of this SF are at the high environment, the high density environment is maybe because of this massive galaxies. So, and this is also kind of consistent with some other previous work where they found higher, more massive galaxies in a dense environment. So, and we also found at this in the deep 2-3 field, we also found very interesting structure where a kind of filament.
Sorry,
Yes.
can I ask a question?
Yes.
So on the on the previous plots, so
Yes.
you're only mapping out star-forming galaxies here. So both your density measurement and your SFR measurement is on star-forming galaxies.
Yes.
Do you have any information on the passive galaxies here? And do you see any sort of passive core for the system? That any sort of incident of higher incidence of massive quiescent galaxies in the center?
Yes. So yeah, sorry. Thanks for question. So in this case, we don't we just focus on the at the resi 1.5. We just focus on the star forming galaxies, and the thing is that like for the quiescent galaxy, I will also come to that part. We also check in the cosmos, and we found the fraction of the quiescent galaxies is very less in this dense structure. But for this case, we didn't check the like when we check the quiescents, there is very less quiescent number of quiescents. But so for the density environment, we just focus on the star forming galaxies, and so it may also be the kind of when we then measure the density, we really need the star forming and the quiescent galaxies. So the reasons may be also because of this, but from the previous work and from my next, which I'm going to show, I found that at this kind of Resi 1.5, the fraction of quiescent galaxies, which is stressed by this O2, fraction of quiescent galaxies is very less. So the reasons, like when I include the quiescent galaxies and without the quiescent galaxies, when I compute the environment, it traces kind of similar structure, which I will show that in the later part in my third project. But for this case, I will just stress that we don't use the quiescent galaxies, and we just focus on the star forming galaxies.
Okay.
Yeah.
Thanks.
So yeah, and yes, we with the because of when after the PFS or something, we can stress more on the found more quiescent galaxies, or yeah, studying more details. And the thing is that at the Resi 1.5, we
And
see.
sorry, one other question.
Yes.
So I guess so. This is O2.
Yes.
O2 is a line that is complicated in that you don't necessarily know it's from star forming processes. And
Yes.
so
That's right.
there can be quiescent-ish galaxies that are emitting O2. Have you done any selection in terms of like UVJ selection?
Yes.
So those contaminants?
Maybe I can just.
I can wait. It's
Yeah.
totally fine.
Okay, I
Thanks
can.
for your attention.
I will come to that part later. Yes,
Okay.
I said it, and the thing is that most of them are not selected by UVJ. So I also check the color like at the Resi 1.5 we have JK, and so then like J minus K, like it will give us more red O2 or not. So in what Hayashi Sans et al. 2013, they also try to find whether the O2 emitters is more red O2 emitters or blue. So from this case, when I say the JK, JZK color, and most of them are kind of bluer. So and from the UVJ, from the Seagull acid fitting, they are fall in the star forming regions, not in the quiescent region. So yeah, for my case, this O2 are coming from this star forming. So this, as you're right, this meant because of this from the star forming region, it may not be necessary that other quiescent or something like that. For my case, yeah. And yeah, so thanks for question. And so at the Resi 1.5, we found very like interesting structure, like where we can this filamentary. And so we want to confirm this structure, and we submitted the proposal. It was accepted. We're happy, and unfortunately, the observation canceled. Yeah. So yes. So up to here, I will next go to the other. We'll jump to the Resi 0.4 for now. So do you have any questions or? from Zoom or? Okay, now I'll go that. Then so now let's try to focus on the like specific clusters and the outskirt and the field. So firstly, so in this from here I will study this galaxies properties in the like dense cluster and the outskirt and the field galaxies, both morphology and the star forming activities. So as I saw before, we can at recipe point 4, we can trace the camera clusters at from our this structure. So this is the already evolved red sequence cluster. So we have this and the cluster. So we try to understand what is the star forming activities and the morphology. And before that, I would like to say that what we use here is only the like star forming galaxies. So in this case, we found lots of quiescent galaxies in the core because this is already evolved. But for our case, we focus only on the like Ice alpha selected star forming galaxies. And so this is a core and outskirt and the field. So we found that less star forming activities in the core compared to the outskirt and the field has a higher star forming activities. So then what we did is that we try to understand, see why this is happening. This may be because this is already evolved cluster. There may be some ramp pressure stripping because when the galaxy is falling into the cluster, it strips this gas, and there are some other environmental quenching effects, which may be the reason why we see this where we less star forming activities in the core. So what we did do next is that we have the narrowband and the broadband images. So suppose here is one example. We have the broadband this is from ICSC, and we have narrowband. So we try to separate the Ice alpha image and the continuum, stellar continuum, based on these two images, like narrow broadband and the narrowband. And then we study the like image fitting, like we do the fitting to see the size. We measure the size of Ice alpha and the continuum. So here is one of the Ice alpha image, and we did the fitting, calculate fitting, and we measure the size. Similarly for the continuum. And what we found is that this is a ratio of Ice alpha and the continuum, and we found that there's truncation of the Ice alpha this in the cluster core compared to the field and the outskirt. So here, yeah, like we found less star forming in the cluster core, and we found truncated Ice alpha this. So this may be because of the ramp pressure stripping, which is involved in this morphology transformation. And so this is just kind of consistent with the hydrodynamical simulations and the other observations, like from Bubble. They did the similar analysis with the Atmos, and we found this kind of less truncation of Ice alpha like this in the cluster core. So yeah, so this may be one of the effects, maybe ramp pressure stripping, where it strips the gases, and when it falls into the cluster core, and so they don't have much gases remaining, and so they're kind of truncation. So yeah, as I will explain about the reason. So when the galaxies in the field were very happy, so this is from the Arisang, this famous cartoon, and when they were very happy, then when they fall into this cluster or group, or so and their gases are stripped away, so they were kind of becoming sad because they're stripped and they are not forming more star. They're forming less star. So this may be the reason why we see this truncation and the less star forming activities in the core. And since this cluster is already red sequence selected cluster, so they are more developed. Yes, so this is at the recipe point 4. Then what happened at the higher recipe?
So Ronaldo, I have a
Yes.
question. So, are you able to in any way look at the star formation histories of these galaxies? And I ask that because I could imagine that a smaller core of H alpha relative to the continuum size of the galaxy could be the residuals of a circumnuclear burst that would come from a tidal event, so some sort of galaxy interaction.
Yes.
And so, I mean, you see that the star formation at the current time is less than the field, but are you able to probe back in terms of SED fitting or something to see if there's any evidence of a burst prior, which may be able to differentiate between ram pressure stripping and some sort of induced funneling.
That's good. Yeah, thank you. So I didn't check it. Maybe I can check those things. Yeah, thank you. Yeah, I didn't check it for now. So I just focus on this. So I can definitely check those and whether they are after starburst or yeah. Thanks. Yes. So any other questions? Then so let's go to the more higher redshift. And so we have very interesting filamentary over density at redshift 1.5, which is stressed by the O2 emitters in the cosmos field. And so, thanks to the cosmos wave, we have like very powerful, like high resolution images from the database cosmos wave team. So yeah, so thanks to the cosmos wave, yeah. So the thing is that we found very interesting structure at the redshift 1.5, which is stressed by the O2. And so here, this is the structure, and these are blues are the kind of O2 emitters, and this magenta square, they are the like spectroscopically like from the diamonds and moss and yeah. So as we can see, there's very interesting structure, and this is the zoom in view like within, this is 1 megaparsec and it's 2 megaparsec. So yeah, so this is very interesting structure, and we try to understand how it start forming activities. And the thing is that I have the plot in the about the I also say the UBJ, and like from the cosmos we had the very wide range of photometric data, and most of the works where they separate the UBJ and the star forming is based on near UB or UBJ. So in our case, I also did the similar, and found that we have very less, like as we can see here, this red are the Poisson galaxies, which is selected from the near UBJ, and with the like between the redshift photometric redshift 1.43 to 1.5, and we found that there is very less Poisson galaxies in this overdense. As we can see, this red are the Poisson galaxies which is selected based on the this near UBJ, and so yeah. So this is also one of the interesting that this structure is very overdense O2 star forming galaxies and very less Poisson galaxies, so they are not evolved yet. So this is kind of structure where we have higher star forming galaxies. So then what we did is that we I checked the here, like I took the cluster core and outskirt, and I took the field galaxies based on the density. Then here is the SFR, which is derived from the O2. As the branch said, O2 may be like from the red or from the star forming. So we also check our emission line galaxies in the near UBJ. We found most of them are located distinctly at the star forming region. So yeah, so we just focus on the SFR, which is derived from the O2 for now, and we found that SFR is more higher in the cluster core, in this overdense core, and we had like compared to the field in the outskirt, and we also did the case test, so it's kind of at the borderline. And in case of the mass, we don't see the significant, but still we have found higher massive galaxies in the core compared to the field. Then we studied the SSFR, where we found that specific star formation in the core is more higher than the field and the outskirt. So this is the reason we obtained, and this may be because at the cluster and the overdense core, there may be some interaction or merger which may trigger the star forming galaxies, or there may be some gaseous galaxies entering which may spark the star formation. So this is kind of potentially a more dynamically active region. And the field galaxies are calmer with a few dynamic activities. So we check how is the merger statistics and the interaction but unfortunately we don't have enough data to say the gas reservoir, which is maybe the future plan to see. And so I did the state move and the Gulf fit also with the from the JWC NIRCam 150, which stress the opticand at the ratio 1.5. So this is the like marginal statistic where we can separate the, and we can see here this is above 0. This is from the lots 2008, and above 0 they are mostly like disturbed or merger, and below 0 are kind of this or other, so non-merger. So and I calculate the fraction of the merger based on this environment, based on this merger statistics, and found that the core galaxies have higher merger fraction than the outskirt, and the field is the lowest. So my interpretation was like that we found higher SSFR in the core, maybe because of this merger, which may trigger the star formation, right? But we found that when I take this merger statistics and our SSFR, there is no correlation. So this may be because there is the kind of the time of after the merger, and the star formation is maybe there is time lag, or we don't know. Yeah. So, but the merger fraction in the core is higher. So, and we check the effective size. This is from the core, based on the core galaxies, outskirt, and the field, and we found that higher like effective size is more in the core and the outskirt and the field, and this is the SSFR with the size. And so here is the red is the core, and this is the field, and we have the outskirt. So there is a kind of, even the number of sample is very less. There is kind of increasing trend where I need to put the error mark, but yeah. So there is higher effective radius. We have more SSFR. So this may be because we have merging after when the galaxies are merged in the core, and leading to more massive and the more size, like larger size, and we have more gases, and this still in these galaxies, and so we found higher kind of this SSFR. That may be the reason why we see higher star forming activities in the core compared to the field and the outskirt. But yeah, so but the thing is that I would like really interesting to study how the gas reservoirs in the core, and also for that we plan to further study those things at the future plan, where we want to study the gas reservoir in the core and the field and the outskirt. Yeah, so this is kind of our future plan for that. Anyway, and we found that when we take the core images, we found that most of the galaxies in the core, which are located in the core, are kind of more disturbed galaxies, more disturbed, and like kind of very small clumps. Like suppose in this case, we see this is just by one galaxy is in the ICSC, like from the Subaru, but here you can see very small, like around the very neighborhood. So this may be the merger, or some clumps together. So this is what this kind of galaxies are mostly located in the core. And for the filament, we see kind of still we also see kind of this disturbed galaxies. This is some of the galaxies, and we found some of them are kind of we found some of them are kind of merger type, or some of them are like not like kind of Norman. So this kind of galaxies in the filament, but in the case of the field, most of the galaxies are very relaxed, and not, we don't see disturbed like galaxies. So this is very interesting that we found this very different from this TWC images. We found the different structure, like more disturbed in the core and kind of mixed in the filament. In the field, most of them are kind of relaxed galaxies. So this may be this is the what we observe. And so what next? This is just in prep. Where we did is that we, as I shown before, we had this kind of clumps, small like two objects. So this is from the ICSC images, and you can see in the ZWST we can kind of separate. This is within the like was like 5 kiloparsec. So this kind of objects we observe. So what I did here is that I calculate the number of this kind of fraction, like how many objects are we can obtain based on the one, like based on the ICSC images. And we found that this kind of clumps or like very nearby neighbor is higher in the core than the outskirt and the field. So which is also consistent with why we see more merger in the core compared to the field. So yeah, the main takeout is that in this dynamically like active overdensity structure, we found more like higher self-forming activities in the core compared to the field and the outskirt. And this is maybe because we also found that higher effective size in the core compared to the field. And we see the most of the galaxies in the core are disturbed compared to the field and the outskirt. So this may be because why we see these results. And yeah, so here is a brief summary of what we observe at the 1.5. And yeah, so for the 1.5, yeah, so as I said, we will like to understand the like coal gas and the other as a future project. But there is a strong dependent on the environment, where like cluster core, filament, the field, they play a very important role in shaping the galaxy's properties. Yeah, so here is a brief summary of what like our methods. So we use the very novel methods which can estimate the redshift and emission line flux, and we can do the 3D mapping, the 3-dimension, and we also separate the structure which can reduce the projection effect. And we can also after that we investigate the projection character environment, and we found like kind of mild increasing in the SFR at the ratio 1.5, and we also check the cluster at the ratio 0.4, and we found the truncation of isoalpha disk in the core, and we have lesser self-forming activities, which may be because of the environment and effects such as run pressure stripping. But at the higher redshift, like when the overdensity structure, which is stressed by only the self-forming region, this kind of overdensity are not evolved, they are very young, so there are more of self-forming activities going on. They don't have, yeah. So yes, so here's kind of my future work, where I would like to understand is that thanks to our this very high resolution images from from the Cosmos, Primer, and the Jet. So next, I would like to study this in order to understand how the galactic structure evolved over cosmic time, like what is the relative role of internet secular process and environmental process, and how the galaxies are regulated. Like, is it within the 1 kiloparsec scale, or is it globally? And also the missing mass problem. So for that, I plan to study the kind of pixel by pixel acid fitting using the ZWST in order to understand, yeah, those questions. And I was interested in like chemical abundance, which I'm kind of my ongoing, which I didn't put it here, but yeah, trying to understand how also environmental independence on this nebular properties. Yes, so this is yeah, my main I would like to understand how the morphology, then self-forming activities and chemical abundance are dependent on environment, and yeah, how they're changing over the cosmic time, like from like redshift 0 to the higher redshift. Yeah, so this is where, and yeah, I personally I'm looking for the postdoc. So if there is anyone who like any leads, it would be nice to thanks to any leads or discussion. So this is it. Thank you so much. And if you have any questions, yeah, please let me know. Thank you.
Questions for Ronaldo, other than questions from me? either in the room or online? Okay, well, I'll take the opportunity to ask another question. You have panchromatic high resolution imaging for
Yes.
the sources that you showed earlier. So the disturbed galaxies in the central regions of this redshift 1.5 structure
Yes.
versus the field.
Yes.
Are you able to see evidence of circumnuclear burst based on, for example, the HST imaging, the colors between HST and JWST?
Oh yes, for that I'm not checking the ICST images for now. Yeah, so I didn't check it yet. So you're asking about, because ICST at the I band it will stress UV, kind of far
Exactly,
UV.
yeah.
So you mean the compare between those and the
Yeah.
yeah.
So the near infrared minus
Yeah.
observed frame near infrared minus
Yes.
optical colors. And so you mentioned doing pixel by pixel SED fitting.
That's my future plan. Yeah,
Yeah.
I'm going to use the ICSC from there to the JWST, like longer wavelength.
Mhm.
Yes, for that I use this is just one example which I'm not properly going to. So for that case, I use the ICSC images and JWST, like different filter images. Yeah.
Yeah, but it seems like you could do that already in this case. So if you take the premise that merging activity is inducing star formation activity, you should be able to see that in the optical minus near infrared colors and the high resolution imaging. So HST to JWST.
Oh, okay, then I can. For now, I didn't focus on. I can check that. Yeah, thanks. So you are saying about how those margin galaxies, when we compare with the far UV and the like near infrared
Res frame optical,
and
yeah.
and the rest of the can
Yeah.
see how
Yeah.
yes, we can. Yes.
Yeah. So any color gradients or anything like that may
Yes.
indicate some star formation activity.
Yes, that's my plan. Yeah, thank you.
Okay.
And this is what I saw here. This is an NUB from the that's 1.5, and here is our emitters. This magenta, and this is O2, and here is the star forming, which is stressed by from this part near UB RJ. So as we can see here, all our emitters are located here. So, and there is not only one which is kind of at about the boundary. So yeah, this is what I was saying. Yeah,
That's pretty good. Any other questions?
yes.
Emma, please.
Just out of curiosity,
Yes.
how excited are you of PFS?
Yes. So that is the major goal which I'm really looking forward. So the PFS, because as I'm also now involved in this making the catalog, because I'm working on the emission line galaxies and we are planning to observe those emission line. So for the PFS is very exciting that at the redshift point at around 1.5 we can have this different line and we can study, and thanks to very wide field we can study how this metallicity or chemical abundance in this overdance and those structure. So this is very exciting, and I hope the PFS will be coming soon, not delay again and again. Yeah. So
They're building it right now, is what I heard.
yeah.
Up at the summit.
Yeah.
This is the month, so all we need is a primary mirror.
Yeah.
Really.
Yeah.
But you also have then you will have a better understanding of what the structure.
Yes, and the constraining structure, and we can also confirm the structure, and study in more detail about the mechanism of physical processes happening in our overdance or field. Yeah, up to the PFS and even moons, because they are kind of complementary. So after this, we can study more with the large sample size and more details analysis. Yeah, so this is very exciting. Yeah. Now I'm involving in this getting the catalog for coming PFS. Yeah. Yeah, so I think any questions there, and we also, I will, this is kind of different project, but I will stop here. Yeah.
So when do you leave, Ronaldo?
I will be leaving Sunday.
Sunday? Okay.
Yeah.
All right. So only a couple more days in Hilo.
Yeah.
Okay. Well, if anybody wants a chance to speak with Ronaldo further, he'll be here this afternoon. And we will also be going out to dinner with him on Friday. So if you're interested,
Yeah.
let myself or Monica know. And with that, let's thank Ronaldo again.
Thank you so much. Thank you so much, Brian, and for giving this opportunity.
Yeah, my pleasure. Thank you for sharing with us.